Okay, so we'll be continuing on this video lecture the sample problem that was cut off in the previous video lecture. So this is video lecture part 2 on our discussion on capacitors and capacitances. Okay, so this is the same problem that was presented from the first video lecture. So a parallel plate capacitor in vacuum, which has a separation distance between the two plates as 5 millimeters, and the given area of the parallel plate capacitor is 2 square meters. Potential difference is subjected between the two plates as given by 10,000 volts, and we are asked for to compute for the following: letter A, the capacitance of the given capacitor; letter B, charge on each plate; letter C, the magnitude of the electric field in the space between them. Okay, so in the first video lecture, you are already presented with the solution for letter A and letter B. So we'll now proceed now with the solution for letter C, the magnitude of the electric field in the space between them. Okay, so this is the same problem that was presented in the PowerPoint presentation, and this would be the solution for letter C. Okay, so first, recall in our previous discussion and previous video lecture on electric potential and electric potential energy, we have presented to you that by definition, the electric potential, which is symbolized by V, is defined as the amount of energy per unit test charge. So that is U over Q sub O. Also, in the same video lecture, you are presented with the form of of computing the electric potential energy between two charges, which is U, and has the form Q sub O over R. Now, if we're going to substitute this form in this given equation, we should have Q sub O over R over Q sub O. Now, of course, Q sub O and Q sub O here cancels each other, so therefore we will have the form for the electric potential as KQ over R. Now, at this point of the discussion, although it is not uh, readily relevant or immediately obvious, at this point I need to mention that we already discussed from the from the topic of the electric field, that the form of the electric field has two forms. One is of the form E is equal to F times Q sub O, and the other one is of the form KQ over R square. Try to notice that the form KQ over R square is almost similar to the form of the result for the electric potential, KQ over R, except for the squared R. So therefore, since our objective for for getting the answer in letter C is the electric field, we need to have the form of the electric field of this form coming from our form of the equation for our electric potential V. So in order to get that, we must multiply a factor between V and this form of the right hand side of the equation, multiplying it with a term which is 1 over R, so that we can make R here squared, so that we can have the form KQ over R squared, so that we can replace this with our form of the electric field. So doing that, what would happen in our equation is that we will have V over R, and this should equal to KQ over R square. And since this is already KQ over R square, which is E, we can replace this as E. So therefore, we will arrive with a relationship between E, V, and R. Now, in terms of the capacitor, of course, E is the electric field existing between the two parallel plates. V is the electric potential that is wherein the two parallel plates are subjected, and R is the separation distance between the two parallel plates. So at this point, we could now substitute the values for V and R. So this is 10,000 volts over 5 millimeters. Okay, so that should give us 2 to the 6 Newton per Coulomb. This is the strength of the electric field between the two parallel plates. Okay, so to continue our discussion, we will now be dealing with the electrical applications of capacitors. Okay, so first is in our discussion is the capacitors in series. Okay, so as we know, capacitors are electrical devices. In terms of its purpose in electrical devices, the purpose of a capacitor in an electrical device is that a capacitor serves as a shock absorber of incoming electrical current and serves as a safety feature for sensitive electrical devices. Much like the shock absorber of the spring system of a car, where this spring system actually protects the car from the shock that it absorbs from a bumpy road, for example. So, in the manner that the shock absorber or the spring system acts as a shock absorber in the spring system of a car, in the same manner that the purpose of the capacitor serves as a shock absorber to incoming influx of electrical current and eventually safeguards the sensitive electrical circuitry in a given circuit. Now, of course, there are many other features, but at the moment, we will be focusing on the analysis, the circuit analysis of capacitors whenever we combine them in electrical circuits. So, in the first combination, the type of combination, we have capacitors in series. Now, when we say two capacitors are said to be in series, they are said to be in line in a connection just like what is shown here in the diagram. Okay, so here is your first capacitor, C sub 1. Here is your second capacitor, C sub 2. Now, of course, if the two capacitors are not yet connected to your electric potential or your voltage, there should be no charge that would accumulate in each of the plates in the plates of each of these capacitors. That means the upper plate of this capacitor and the lower plate should have no charge. That means there is no net charge in each of the capacitor. This is neither negative or positive. The same goes with C sub 2. Until such time that we connect the combination of capacitors to a potential difference or a source voltage, that is only the time wherein the capacitor would have its corresponding negative and positive terminals. Okay, so how do we connect given capacitors in series? Okay, so to connect them in series, what we do is to make or establish a connection using a conductor connecting one terminal or one plate of the capacitor to the other plate of the second capacitor, and connecting the other end of the capacitor to the one of the terminals of the power source. The same goes with the other end of the first capacitor, connecting it to the other terminal of the power source. Okay, so for example, if A here is actually the positive terminal of our power source, B would be the negative terminal of the power source. So the tendency, if this is positive and this is negative, what happens here is that since this is positive, the tendency is for this terminal to attract electrons towards it from the upper plate of the first capacitor. So the negative charges would actually flow towards this direction, leaving a positive net charge on the upper plate of the first capacitor. That is why in this illustration, the upper plate of the first capacitor is labeled positive because of the deficiency in electrons. Now, the electrons would transfer to or will be attracted towards this direction. Now, to continue, what happens now is that there will be a net positive charge on the upper plate of the capacitor, And since this would be positively charged, in effect, it would repel or induce a repulsion of the or attraction. It would actually attract the positive, the negative electrons in our lower plate capacitor, and repelling actually the positive charges towards this direction, thus leaving a negative net charge on the lower plate capacitor. Now, of course, the number of electrons that will be deficient in the on the upper plate would correspond to the number of electrons that would accumulate on the lower plate of the capacitor. So that means the net charge on the upper plate would be equal to the net charge of the lower plate. Now, of course, what happens here once these two charges are established on the upper plate and on the lower plate, this process of induction continues up to the second capacitor. Since the tendency is that the upper plate repels the protons on the lower plate, these protons would actually accumulate at the other end of the plate of the second capacitor. Now, since the upper plate of the second capacitor would have a net charge of a positive net charge, positive Q, now in essence, this positive charge would attract electrons on the lower plate by induction and pushing away the negative net charge towards this direction, thus having a negative net charge on the lower plate of the second capacitor. And if you're going to connect another set of capacitors to continue this process would actually go indefinitely for as long as the capacitors are connected to a voltage source. Now, the idea here is that when you have capacitors in series, the amount of charge for the capacitors in series that would accumulate in each capacitor is the same. That means the number of charges that will be accumulated on the first capacitor is the same as the amount of charge that would accumulate on the second capacitor, and so on if you still have a set of capacitors that will be connected in series. For as long as the capacitors are connected in series, the amount of charge that would accumulate in each of the plates of each of the capacitors would be the same. Now, it follows if you have a common value for the charge that will accumulate on each of these capacitors, and perhaps you have different values for the capacitances, it's likely that the values for the voltage across each of the given capacitor would be different for each capacitor. Okay, so in a series connection, the magnitude of charge on all plates is the same. Potential difference across each capacitor need not to be the same. Now, in order to get the overall effect of the capacitors in series, of course, an overall effect means that there is an overall equivalent value for the capacitance equivalent to the combined effects of the two capacitors in series, and we call this combined effect as the equivalent capacitance, and this equivalent capacitance refers to a replacement of the two capacitors by a single capacitor that has the same amount or capacity as the combined effect of C sub 1 and C sub 2. And we call this the equivalent capacitance. Now, in order to compute for the equivalent capacitance in series, the formula for computing for the equivalent capacitance of capacitors in series would have the form 1 over C equivalent is equal to 1 over C sub 1 plus 1 over C sub 2 plus 1 over C sub 3 plus and so on and so forth, depending on the number of capacitors that we connected in our circuit in series. Now, as mentioned before, the amount of charge that accumulates on each of the given capacitors is the same for all the capacitors. So therefore, Q sub 1, meaning the charge on capacitor 1, is the same as the charge accumulated in capacitor 2, is the same as the amount of charge that would accumulate on capacitor 3 and so on. Okay, in terms of voltage or potential difference across each of the capacitors, the amount of voltage is dependent as presented in the form of our definition of the capacitance. C is equal to Q over V. V is equal to Q over C. Each of this voltage does not necessarily be equal to each other, but is dependent on the amount of charge accumulated on the capacitor and the value of the capacitance of the given capacitor. Okay, so let's have an example. We have two capacitors in series. One is C sub 1 with a value of 6 microfarads and C sub 2 with a value of 3 microfarads. They are connected in series and they are connected to a power source or a voltage source with a given value 18 volts. So what is asked in this given problem is the value of the equivalent capacitance, the value of V sub 1 and V sub 2, and the value of the charge that would accumulate on each of the given capacitors. Okay, so for the solution, we look at this document. So we have the same problem that appears in our PowerPoint presentation. So we proceed with answering letter A. Okay, so again, to compute for the equivalent capacitance, we have the form of the equation of the equivalent capacitance as 1 over C equivalent equal to 1 over C sub 1 plus 1 over C sub 2. Okay, so substituting the values 1 over 6 microfarads, 1 over 3 microfarads, this is being summed so that you will be using the sum of fractions. So you should be able to get 1 over 2 microfarads. Now remember, this form of the equation is equivalent to 1 over C equivalent is equal to 1 over 2. This is 1 over C equivalent, not C equivalent. Okay, so to get C equivalent, we should get the reciprocal of this form of the fraction. So getting the reciprocal of 1 over C equivalent gives us C equivalent, and correspondingly that gives us the reciprocal of 1 over 2 microfarads, which is 2 microfarads. Therefore, the C equivalent or the equivalent capacitance of the two capacitors in series is equal to 2 microfarads. Try to notice the value and try to notice and compare the values of the equivalent capacitance as compared to the individual values of the capacitances. Look, this is 2 microfarads, this is 6 microfarads, this is 3 microfarads. They are combined in series so that we can have 2 microfarads. Between these three values, which among them is of the least or the smallest of value, and which is the greatest of value? Of course, 6 microfarads is 6 to the negative 6. 3 microfarads is 3 to the negative 3. And 2 microfarads is 2 to the negative 6. 3 microfarads is 3 to the negative 6. So therefore, among these three, 6 microfarads is the greatest value, and 2 would be the least of the values. So therefore, by this observation, we can say that when we combine capacitors in series, what we actually achieve is that the combination of the capacitors actually renders a lower value as compared to the individual values of the capacitances. So this means that for constructing electrical circuits using capacitors, if it is not available, if a desired capacitance is not available in the market, and you want what is available in the market is actually large values of the capacitances, but you want in your application a lower value of the capacitance. So what we can do is combine the available values of the capacitances in series so that we can have a lower value of the capacitance if that lower value is the desired value of the capacitance. Okay, so next we proceed with with letter B. So what is asked in letter B is the values for the individual voltage across each of the given capacitor. Now, before we proceed further, let us take note first that the C equivalent, or the equivalent capacitance, is also equal to the overall charge that is stored in the combination of the capacitor divided by V sub AB, or the voltage across the given circuit. So that means if you're going to compute for Q would be equal to C equivalent times V sub AB. If we're going to compute this would be equal to 3.6 to the negative 5 coulombs. Now, why do we need to take note of the value of the total amount of charge stored in the combination of the capacitors? Note that Q1, or the charge stored in capacitor 1, is equal to Q sub 2, which is the charge stored in capacitor 2, is equal to Q for the capacitors, or for any capacitors connected in series. So therefore, we can now proceed with computing for the individual voltage across each of the capacitors, since we are already given the values for the charge in each of the capacitor. So that means V sub 1 is equal to Q sub 1 over C sub 1. So Q sub 1 is 3.6 to the negative 5 over 6 microfarads, so that gives us 6 volts. V sub 2 is given as Q sub 2 over C sub 2, 3.6 to the negative 5 over 3 microfarads. That is given as 12 volts. Now take note, how do we know if our answers is correct? Take note that in the given circuit, the circuit is connected only to a power source which is 18 volts. So that means if you're going to compute individually for the voltages across each of the given capacitor, the sum of the voltage of each of the given capacitor should not exceed the available energy provided by our voltage source. Remember that the voltage source is our source of energy for the electrical connection. So that means the sum of the individual values, if we're going to get the sum, should not exceed the available energy provided by our voltage source. So that means if you're going to add 12 volts with 6 volts, that should give you 18 volts. And this value should not exceed 18 volts, since 18 volts is the only amount of energy input. Okay, so for letter C, we're already done, since we already noted that Q sub 1 is equal to Q sub 2 is equal to Q is equal to 3.6 to the negative 5 coulombs. Okay, so next in our discussion would be capacitors in parallel. Okay, so capacitors in parallel connection, what is common among the capacitors in parallel is that from this illustration, try to notice that the plates of each of the given capacitor has a direct connection to our power source or voltage source. So for example, for our C sub 1, the positive terminal of the capacitor has a direct connection to point A. The same goes with our C sub 2 or capacitor 2. It has a direct connection to point A. Now for C sub 1, the lower plate, it has a direct connection to point B. The same goes with C sub 2. The lower plate has a direct connection to point B. So what does this mean? This means that whatever value that we assign for our input voltage, that input voltage would be the same voltage that would register across the first capacitor and the second capacitor, simply because each of the given capacitor has a direct connection to our voltage source. So this means that V sub 1 is simply equal to V sub AB, and V sub 2 is equal to V sub AB also. Now, although the voltage could be is the same for both capacitors in series or in parallel, it doesn't necessarily mean that the charge that would accumulate on each of these capacitors would be the same for both capacitors. Okay, so we have the equivalent form for the equivalent capacitance for parallel. So simply, if we want to get the equivalent capacitance of the combination, we just simply add the values of the capacitances of all the capacitors in parallel. Now, what is common again for capacitors in parallel is the voltage source. So V sub 1 is equal to V sub 2 is equal to V sub 3, or any number of combination is equal to V sub AB. Okay, so let's consider again this problem. Okay, so we have C sub 1 again as 6 microfarads, C sub 2 as 3 microfarads. They are connected in parallel to a voltage source 18 volts. So again, we are asked to find the equivalent capacitance, the voltage across each of the given capacitors, and the charge that would accumulate on each of the capacitors. Okay, so for the solution, we have this one. Okay, so to compute for the equivalent capacitance, simply we just add the two given values for the capacitances. So that is 6 microfarads plus 3 microfarads, so that is given as 9 microfarads. Now for letter B, we are asked to get the values for the individual values for the voltage across each capacitor. Now take notes that since V sub 1 and V sub 2 is equal to V sub 2 is equal to V sub AB, therefore this is equal to 18 volts. V sub 1 is 18 volts and V sub 2 is also 18 volts for capacitors in parallel. Now therefore, we can now compute for individually for the charge that would accumulate on each of the given capacitor. So Q sub 1 is given by V sub 1 C sub 1. This is 18 volts multiplied by 6 microfarads. So this is given as 1.08 to the negative 4 coulombs. Q sub 2 is V sub 2 C sub 2. So this is 18 volts times 3 microfarads. So that is given as 5.4 to the negative 5 coulombs. Okay, so last leg of the discussion is capacitors in combination. Of course, in reality, we do not simply combine capacitors in simple combinations such as series and parallel, but most of the time they are actually combined in combinations of series and parallel, and at other times they are combined in combinations that are neither series nor parallel. But at the moment, we will not be concerning ourselves with combinations that are neither series nor parallel, but we will be limiting our discussion on the simple combinations of series and parallel. Okay, so what we can see here in this illustration is that the capacitors are actually connected in both series and parallel, but particularly this capacitor and this capacitor are connected in series. This capacitor and this capacitor are connected also in series among themselves. The upper combination and the lower combination are actually connected in parallel. So take note, what skills that you need to assimilate in this discussion is the skill of identifying what combination is presented in the combination of series and parallel connections. So this is a key skill that you need to acquire, the skill of identifying the type of combination that exists between circuit elements such as capacitors in series and capacitors in parallel. Okay, so I will not be presenting to you the solution for this example. I'll be asking you to answer the value of the C equivalent of the system. So this would serve as your exercise, and I expect that you will be submitting the solution for this given circuit by Friday. That would be Friday, April 29. Okay, so again, this is part of your exercise. This is C sub 1. These are the given values for the capacitances C sub 2, C sub 3, C sub 4, and C sub 5. Okay, so but for this given exercise, I will be presenting. I will be the one who will be identifying the combination. So, what I'm asking you are is for you to simply compute for the equivalent capacitance, as long as you know the type of combination that exists between the capacitors, you should be able to compute the equivalent capacitance for those part of the circuit until you arrive with the last combination of the circuit. Okay, so probably you could start with combining C sub 1 with C sub 2, or you could also start with combining C sub 3 with C sub 4. Okay, so try to notice that the type of combination that exists between C sub 3 and C sub 4. C sub 3 and C sub 4 is actually connected in series. So therefore, the formula for series, you will be applying the formula for series in for for the combination of C sub 3 and C sub 4. Now, once you have combined the two capacitors C sub 3, C sub 4, you could replace the combination by a single by a single capacitor representing the value of the combined effects of C sub 3 and C sub 4, after which you determine what type of combination is the that equivalent capacitance as compared to the rest of the circuit. Now try to notice that C sub 1 and C sub 2 are combined in parallel, and they are also combined in parallel with the combination of C sub 3 and C sub 4. So that means this overall rectangle here, you will be applying the formulas for capacitors in parallel. And finally, once you have combined this upper portion of the circuit, representing it using a single capacitor, try to notice what the resulting circuit, comparing the resulting circuit with the rest of the combination of the circuit. So finally, you should arrive, or you should represent this with a single capacitor. And that combination is actually in series with C sub 5. So with this description, I hope that you should be able to get the uh, answer for the combination or the equivalent capacitance of the given circuit.